series and convergence, how to apply the nth term test for divergence. That's the key in terms of what we want to use and what we're looking for. It starts, however, a little bit different. The theorem, the major consequence in mathematics is the theorem that talks about the limit of the nth term of a convergent series. This theorem here. Now it says this, that if the series converges, then the limit of the sequence is equal to 0, which is a fascinating conclusion. However, it tells us nothing. We can't use that. What are you going to do with that? I don't know. But the contrapositive of this theorem is most interesting. The contrapositive of a statement simply says that if you have the statement, that is, P implies Q, if P, then Q, where P is said to be the premise and Q is the conclusion. If P, then Q. If P, then Q. If P implies Q is true, then the contrapositive is equal and also true. The contrapositive simply says that you reverse the statements, which would be the converse, but then you negate them. The converse is not necessarily true all the time for any type of statement, whether it's mathematical or it's just any statement, doesn't matter. Logic, reason teaches us that. But the contrapositive is true if the original statement is true. The contrapositive is false if the original statement is false. The contrapositive of this statement says, well, the statement here says if P, what is P? That the series converges. Then Q, the limit of the sequence, equal to 0. So if not Q, then not P. That is, that if the limit of the sequence is not equal to 0, then the series diverges. That's what we want to use, and we call that the nth term test for divergence. It is written here really as a corollary. A corollary just relates from a major consequence. Theorem 9.8 is the major consequence, and then we have a corollary or a lemma, another phrase, L-E-M-M-A, a lemma, which when I was driving my lemon car in college, I could definitely relate to that. So here we use this, that if the limit of the sequence is not equal to 0, then the series diverges. Fascinating. All right. So for this problem, you check the limit of the sequence. So here, notice that the limit as n goes to infinity of n over n plus 1 is equal to 1. Right? It's not equal to 0. Well, this implies by the nth term test that the series Now here's the thing. If the limit of the sequence is equal to 0, you can't use the nth term test. Here this says that the premise has to be true. If the limit of the sequence is not equal to 0, then you can make this conclusion that the series diverges. Right? But if the limit of the sequence is equal to 0, do something else. You can't use this guy. Right? It's not applicable. Same thing here. That and you're not looking for the limit of the series. You don't know what that is. Right? You're dealing with the sequence. A series is the sum of sequence values. So here, the limit as n goes to infinity of n squared over n squared plus 1 is equal to 1. It's not equal to 0. Thus, by the Nth Term Test, the series diverges. Same thing here. Is there another one? There's one more down there. Here the limit as n goes to infinity of n plus 10 over 10n plus 1 is equal to, and what I'm using for all these three is looking at the horizontal asymptote that we had a concept that said that if the power of the numerator is equal to the power of your denominator, the horizontal asymptote translation limit is equal to the ratio of leading coefficients 1 divided by 10, which is this one. Okay, the point is not equal to 0. This implies by the nth term test, the series diverges. Now sometimes a series might not be so easy to determine whether or not the its sequence values diverge. So we might have to take a closer look. So here, look at this, the limit as n goes to infinity of n over the natural log of n. N over the holiday n. No, n over the natural log of n. Well, that's pretty good funny. Well, is this equal to 0 or not? Well, I don't know. Well, let's look at it. Here, as n goes to infinity, the numerator goes to infinity, and the natural log of n also goes to infinity. So here, we have infinity over infinity. And whenever you have that, what do? Do you remember? Yes, you said it right. It's an indeterminate form. We use one of three things. We can either factor, rationalize, or use L'Hopital's rule. Well, you can't factor, can't rationalize, so we use L'Hopital's rule. It's time to go. So this is the limit as n goes to infinity. Take the derivative of the numerator, that's 1. Take the derivative of our denominator, that's 1 over n, times the derivative of n, which is 1. This is the limit as n goes to infinity of n. That limit is equal to infinity. Here's the thing, it's not equal to 0. So then here, by the nth term test, the series diverges. Pretty cool. I'll see you around.